Again, good afternoon, everyone. Thank you for joining us for the last lecture for this term. The last lecture for this term is entitled An Introduction to Residual Learning for Computer Vision. This would be presented by Aaron Gabriel Dichoso. So let me read the abstract of the lecture for today. This online lecture will cover residual learning, a practice widely utilized in computer vision networks. Attendees will learn the concept and the math behind residual learning, the research that brought about the breakthrough, and innovations and application brought about by the architecture. So if you're familiar with the term residual learning, this is actually a very important work in computer vision back in 2015 that enabled us to train very large networks. Okay, so the presentation will cover the following: the definition of residual learning, computer vision before residual learning, creation of residual learning, how it was designed, the math and architecture of residual learning, and what happened after introducing residual learning for computer vision. So let me introduce our speaker for this afternoon. Aaron Gabriel C. Dichoso is currently a fourth-year computer science student at DLSU University under the BS-MSCS Honors Program. As a member of our lab, the Center for Computational Imaging and Visual Innovations, his laboratory experiments focus on camouflage crop detection with an interest in pursuing the improvement of camouflage detection architecture for his thesis research. So without any further ado, let me give the floor to Aaron. Aaron, you may now share your screen.
Hello, everyone. So once again, thank you, Sir Aaron, for that introduction. And as Sir Aaron said, I'm Aaron Dichoso, and this lecture is going to be about residual learning. And I just want to remind everyone that this lecture is going to cover some concepts regarding machine learning that I hope everyone is familiar with, such as neural networks, the training process, and most especially backpropagation and the math behind it. So this lecture is going to cover just what residual learning is and the background of computer vision before residual learning was ever introduced, and then how it came about, the architecture behind it, the performances that were gained during that research, and finally the applications of ResNet or residual learning networks. So before we really dive deep into residual learning, I want to ask you guys this question for just a small icebreaker, okay? So what hobbies have you recently picked up, and how did you go about learning these hobbies? So I just want you guys to type these into chat and just like have a really short response to it. And I just want you guys to keep this in mind in the back of your heads while we're talking about residual learning. So here, Kate says drums. She learned it from YouTube. I have an example right here. So I used to play guitar back in senior high school. However, due to like college requirements and things like that, I recently didn't have the time. So then I started going back again and like trying to learn guitar again. So the way I went about it is I started learning the old songs that I used to play. So things like Green Day and things like that. So that's how I recently got back into learning my hobbies. And basketball, sabi dito ni Ice, basketball by playing it and watching other people play it. So I know some of you guys also have answers as well to this question, and I just want you to keep that in mind while we talk about residual learning. Okay, so let's talk about computer vision first as a field. So computer vision is just all about leveraging image data for computers to solve real-world problems. So here I have an example of a computer vision task called object detection. However, other tasks also include image identification or like giving a label to the primary concept that the image is showing, object detection, as I showed before, and object segmentation. So all of these technologies back in the 2010s revolved around the usage of convolutional neural networks, or CNNs. So CNNs, or convnets, as some people would call it, are a type of neural network that uses convolution operations to manipulate image or matrix data. So as I'm sure all of you have a background in, images consist of 3 channels RGB, and those 3 channels have values between 0 and 255, right? And these image values are organized in a matrix, an X and Y matrix, width and height. So this convolution operation manipulates these values using a sliding kernel or filter. So many different operations can be done using this sliding kernel. So for example, here I have an image and I applied this specific kernel right here that detects and filters only the vertical lines being found in the image. So the specific values of this kernel is learned through training. So when you train the convolutional neural networks, it is going to find the most optimal values inside this kernel for your specific computer vision task. So back in the early 2010s, as I said, these convnets, or CNNs, were the main foundation for the architecture for solving the task. And models during this time focused on improving image classification performance by creating deeper and deeper neural networks. So for example, here it's VGG19, one of like the state-of-the-art models during that time for image classification. And what they did is they utilized multiple convolution operations in order to achieve their state-of-the-art performance during that time. However, as researchers started creating deeper and deeper neural networks, two highly concerning problems emerged. So first here is the vanishing or exploding gradient problem, where as you go deeper in a layer, the gradients either go exponentially high or exponentially low and affect the weights of the initial layer very negatively, or here the network degradation problem. So let's start first with the gradients problem. So let's just slow things down and just talk about the training process for a neural network. So when you have, for example, an input image and you're passing it through here, this is just some sample CNN that I have with 3 convolution operations. These convolutions have randomly set weights at the beginning. So these weights are the values inside the filters. And as the input image goes through these convolutions, it's going to output a new image or a new prediction. So you take all of the predictions during your training process, and then you compare that with the ground truth of the training data, and that's how you compute for the loss. Okay? So I hope this all sounds familiar to you so far regarding the training process. And after you take the loss, you then backpropagate this loss value throughout all of the operations or layers that you have in this neural network. And as you propagate these values, the filters or the weights of the network are updated accordingly. So that's just a background of how backpropagation works, right? So backpropagation is done using calculus. And this is because here, for example, here for B, when you're trying to update the values here, you are using gradient descent and computing for the specific gradient as to how this specific layer affects your output. However, this layer here, for example, layer B, the outputs here have to go through another function or another operation, layer C. So accordingly, right, when you're computing for the derivative of a function inside the function, you have to use the chain rule. So that's why when you're hearing things about how gradient descent works, you usually see these kinds of operations in calculus. So the derivative of y, or the output, with respect to the operation b is equals to the derivative of c with respect to operation b, and the derivative of y, the output, with respect to the operation c. And that continues on as you go deeper and deeper and deeper throughout the layers until you eventually reach here, the input image, and you don't have any more weights to update, right? So you are adding on more and more multiplication operations as you go closer and closer to the start of the neural network. So two very concerning scenarios may occur when you do this process for backpropagation, right? So number one, either as you go closer and closer to the start of the network, the gradient becomes smaller and smaller. It shrinks exponentially. So this means that at the start, the layers at the start of the neural network will experience little to no weight changes. Thus, it is labeled the vanishing gradient problem. At the same time, you can also have a scenario where the layers in the neural network keeps on multiplying bigger and bigger numbers. So you get bigger and bigger gradients, thus resulting in larger weight changes at the very start of the network. So this is called the exploding gradient problem. And both of these problems are bad because they can affect the overall accuracy of your network. As you could imagine, if you have little to no weight changes at the start of the network, you are also going to experience little to no effects in the training accuracy. And at the same time here, you could actually overshoot the weight changes and have negative accuracy, negative effects into your training accuracy. These two problems have somewhat been mitigated already by normalization methods. So when you're here initializing the weights at the start with random values, you just have to normalize it. And after every operations or so, some number of operations, you just do some batch normalization where you ensure that all of the outputs are in between 0 and 1. So that sort of mitigated the problem. However, this problem, the network degradation problem, this was found by He et al. From Google during the 2016 time. And what they found is that when you try to increase the number of layers in the network, there's eventually going to come a point in time where you try to increase the number of layers and it doesn't increase the accuracy anymore. So as it says here, increasing number of layers in the network saturates training accuracy. So as you can imagine, when you try to increase the number of layers even further, this accuracy actually starts to degrade. So like it doesn't make sense, right? You're trying, recent trends have showed that when more layers means better accuracy. However, here it's telling us that there's a point in time where we cannot increase the number of layers anymore to improve on accuracy. So it's sort of how in this time they hit a roadblock. We could not improve performance anymore by increasing the number of layers. So there comes the limitations of the convolutional neural network architecture. How do we improve upon these limitations? Here then comes residual learning. So let's talk about these architectures for a bit. So this is the example of a plain CCN architecture. So this was the architecture being used before residual learning was implemented, okay? So Here we have certain groups of convolutional operations, and what is being done for these each of these groups is each of them are like being assigned some sort of desired transformation. So imagine I have an image here, and then I pass it through these two blocks, and maybe I'm hoping, okay, this will isolate all the edges found in the image. Then after that, after isolating the edges, maybe this one is going to isolate the shape. So these two layers are actually performing the same convolutional operations. And then the hope is that they will eventually map to a desired transformation that you want in order to get the prediction or performances that you want. However, here comes the first limitation of that architecture. It is hard for groups of blocks to optimize for an identity transformation. Why is that? Well, if you were to go back to what I said earlier, each of these convolutional neural networks have filters to them. And for you to do an identity operation, the filter of this first convolutional operation needs to be canceled or offset by the other layers inside of this group. That's how you would do an identity operation, diba? Either that or both of them result into zero. And those two are actually really hard to do. I like to imagine it as this. Have you ever guys played like the telephone game, for example, in Christmas parties or diba sa mga intrams? So you send a message to someone, you whisper it, and then or either everyone has like their ears closed, and then you try to send a message to that person, and then eventually at the end, the goal of the person at the end is to get the original message. So just like how this is like really hard because nobody is hearing what the first guy is saying, and eventually the context gets lost at the very end. See, convolutional neural network blocks at the same time in this architecture are experiencing the same problem. They are finding it really difficult to optimize for the identity transformation or just returning the original message through the blocks because they do not have a reference to the original data or the input that was given at the very start of that group. Okay, number two of the limitations, each group of blocks needs to learn a completely new transformation to perform. So I'm sure naman that's like obvious here with the diagram. As I explained before, each one is being put into the network so that hopefully some new transformation occurs in the image. However, He et al., the creators of ResNet, argues that learning the difference between two images, so that task is called the residual mapping, is much easier to perform than learning the transformation from one image to another. So instead of learning what the edges of the image is, what if each neural network just learns how to find the difference between the image here and the expected image at the end, right? So going back here to the question I asked earlier, what hobbies have you recently picked up? So when you were learning your hobbies, what method of learning did you find easier? So for example, some people would actually learn their hobbies like from the very beginning, starting at the foundations. So going back to my own hobby of learning the guitar, I learned that some people actually like started learning from the guitar at the very bottom of the foundation. So learning how to read notes, learning how the chords work, learning how what each note sounds like, and like hear what each note is best suited for a group for a major scale, ganon. And when you're learning like that, it's like really overwhelming at the beginning, right? So what some people would do, so what I did actually, instead of learning like that, I learned from what I know and I explored from there, right? So instead of learning all of those foundations at the beginning, I just said, okay, I have a guitar, I want to learn. Okay, what's my favorite songs to listen? And then that's where I picked up. So yun. So like now I play and I understand how it works. And then from the very beginning, I didn't understand. Tapos I understand like from learning these songs. Okay, what's a chord? What a chord is? What does it look like? What does that sound like? Okay, here now I have a different chord to learn. And then there I learned all the different things along the way by small and small adjustments. So that is what residual learning is. Um, that's kind of like an illustration of what residual learning is. So instead of learning from the very, very bottom, so instead of learning from the very, very foundations, you're just learning what's the difference between what you know already and what needs to be learned, right? So that is the residual learning. And this allowed for networks to be much more easily trained. So since this is a much simpler task to learn for convolutional neural networks, it allowed networks to eventually be trained to be deeper and deeper. So it's kind of like removing the bottlenecks in learning during here, for example, here using plain architecture and like easing up the learning process here so that you can make deeper and deeper networks. And residual learning is implemented through the creation of shortcut connections. So if you look at the differences between this architecture and this architecture here, the only difference that they put is that between each group of convolutional neural networks, a shortcut operation is implemented by just adding the value of the original image to the output of the group. So the question is why does that work, right? Parang hindi ba parang ginawa-gawa lang nila yon? Well, there's actually some math behind that architecture. So let's dive deep into that math. So here I have the formula, just like a sample formula of what a plain architecture would look like. So plain architectures have this sort of target function. So they have a function to perform with some weights. And hopefully, when you adjust these weights, it gets close and close to here, h of x, which is the target function. So just straight down. Now, residual learning architecture argues that instead of learning this itself, the target function itself, you are learning the difference only between the target function and the original input image. So that is what did they find here instead. So this is saying that I am now updating the function that the convolutional neural networks will do from here, just learning the target function to learning the difference between the target function and the original image. So this is the residual. That's why it's called residual learning, because you're only learning just the adjustment between the function and the original image. Now, simple algebra would tell us, okay, we can move this x to the right, and then now we have redefined what the target of your function is. And that is why we are utilizing the shortcut connections here. That is how it was conceptualized. So before I move on, is everything clear so far regarding residual learning? Can I see like a thumbs up or some chat? Okay, thumbs up. Thumbs up. Okay, that's good. So we'll save all the questions for the lecture for later. But for now, let's move on to how the differences in this architecture actually also affect the backpropagation process. So here for the plane architecture, as we discussed before, this is the function for the network. And then after you take the predictions, you compute for the loss of the predictions with the ground truth, right? And then after that, you compute for the gradients of the loss with respect to the inputs. And it would actually look like this because you are going through a function, right? Parang chain rule lang ulit. And since f of x, y is equals to f of x, therefore the derivative of the loss with respect to x is equal to derivative of the loss with respect to y times the derivative of y with respect to x. So parang simple chain rule lang yun, okay? However, here for residual learning, we have this additional term plus x now. So this affects the computation for gradients for backpropagation as such. So here we still have the main base function here. These two are very similar. However, if we look back, what is y in this model prediction? So this y refers to the predictions. So it is f of x plus x. So I just write that down here. And as we see, we actually have an identity term. So this is the derivative of x with respect to x, which we know is always just going to be 1, right? So I wrote I here because x is a vector. So I is just like the representation of 1 as vector form. So that means when we're computing for gradients in backpropagation, it is much easier to learn identity transformations because it is just built in already in the backpropagation process. Nandito na yung identity transformation. And all the neural network has to do is realize, oh, okay, you want identity transformation. I just set this term to 0 and we're all good. So this also prevents risk of vanishing gradients. Now, your first problem, so that's actually just like a side benefit, because now even if this value becomes really, really small, we still have this identity matrix value to compensate for really, really small gradients. And this means that the gradient only has to adjust according to residual. So overall, that's what it means here. And that means it is like much easier to perform the training process as a whole, as opposed to the plain architecture. Okay. Now we actually move on to the types of residual networks that were tested in that paper. So this is the figure that was given from He et al. And I just translated this into a much better diagram for us to visualize and understand. So these are just like different flavors of ResNet, as they call, or residual network, that they tested during that paper. So here, each number here just refers to the number of layers that were implemented for that specific type of ResNet. So we have ResNet 18, 34, 50, 101, and 152. And as we see here, it is very similar to the plain architecture. However, it just includes the addition of shortcut connections for each group of convolutional neural networks. So let's start first with the ResNet 18 and ResNet 34. So it consists of 2 convolutional neural network layers for each block, for each group, and with a shortcut connection between them, because from their testing, they found that 1 layer per group or block gave no improvement. So they tested 2 blocks per group instead. And just just to give us an understanding of why this architecture is made this way, this is done in such a way that the image is at the top, and then as it goes through each type of block, it actually lowers in image resolution size while increasing yung number of channels or dimensions. So if the image here started out as 256 by 256 at the top, it goes to 128 by 128 at the bottom, and then 64 by 64, 32 by 32, all the while increasing the number of channels. So this is just giving it more and more information for the residual network to learn. And finally, these last four layers at the bottom is just used to give the final prediction, which is yun nga, image classification. Now, ResNet 50, 101, and 152 are very similar. However, the only difference is that they use 3 blocks per group instead of 1 block per group. So each one of these does a different thing. The first block is just to scale down the size. Then the 3x3 here sa gitna, in the middle, is used to perform the feature extraction. So this is what actually learns the features or creates the transformations being used in the image. And finally, this one, the last one, is just another layer to scale back the original image size. So the differences here is that in ResNet 18 and 34, there's 2 layers that are learning different transformations. And ResNet 50, 101, 152, there's only 1 layer that is actually learning the transformations. So these 2 layers are actually done yung 1 by 1 convolutional layers for each group. It's just done for efficiency reasons because they found that it's much more efficient to do this than to do some other method like linear projection. Mostly because just of the sheer depth that these layers have. So for example, this one has 152 layers, which is parang unheard of at that time. A bit, yeah. And finally, let's talk about what results they actually brought about. Okay. So ResNet performance, they tested the performance of ResNet by comparing it with plain CCN architectures. They're plain equivalents right here. So the only difference is that ResNet has shortcut connections per group and plain does not. And they tested it using the 2012 ImageNet dataset. And as explained earlier, the goal of ResNet is to solve the network degradation problem. So the network degradation problem, as explained, whenever you try to go any deeper than what is shown or tested, you start to experience training accuracy losses or negative effects on training accuracy. So what they want to show here is when you compare ResNet 18 to ResNet 34, ResNet 34 should have less errors than ResNet 18. And when you compare plane 18 to plane 34, plane 34 should have more errors than plane 18. Parang ganon. And that was what they saw actually here. So this is adopted from the paper. And as we see here in the plane 18 figure, so even though plane 34 has more layers, overall, it has higher errors. So in here, higher is bad because that means error rate. And in here, even though less layers, see plane 18, it has higher, less errors as well. So that is showing the network degradation problem. On the other hand, ResNet 18 has error rates here, but when you go down to ResNet 34, it overall has lower error rates compared to ResNet 18. So that means that they actually solved the network degradation problem. And we can now are able to train deeper and deeper and deeper neural networks past this point. Parang ganun. Additionally, this is actually parang flex lang din nila. ResNet results obtained first place during that time in the ImageNet large scale visual recognition challenge of 2015, where it's actually pretty significant because they only got 3.57% test error rate. So as you can see here, all of the other state-of-the-art networks, they got errors around 7% to 5%, and uh, around 2% performance increase in terms of error rate. That is very significant for them because that means that we are able to now train our networks to be better performing overall. So parang it's opening up a new door for researchers to be able to train better and better neural networks. Fine, yeah. So examples of this here in terms of performance, applications. So this is a feature pyramid. So they actually found that when you're using ResNet, each group of blocks in ResNet, it corresponds to a different type of feature in a different type of feature in the neural network. And by taking these different types of features, you are able to make different sorts of predictions for each layer. So in here, actually, they also adopted yung shortcut connections. And basically, this is just showing na you are able to have better explainability in the actual training process for convolutional neural networks. Additionally, a part of that is object segmentation, which neural ResNets actually also enabled by here. This is called mask RCNN. It derives from another neural network called faster RCNN, where they use ResNet as something that is called a backbone. So actually, the main contribution of ResNets today in these applications is becoming a backbone for new networks. So when you say backbone, it's actually a term for computer vision, where it's some sort of specific network that is being used to extract features from images or your initial data. So these networks use ResNet as a backbone to be able to extract features and apply them for their specific use case. Additionally here, this one is a neural network called UNet++, and it uses, in here, this diagram. This uses ResNet as a backbone as well. Additionally, not only that, they were also inspired by ResNet themselves by using skip connections in their architecture also. So as you can see, there's like double inspiration from ResNet here for medical imaging, for specifically finding polyps inside of cells. And finally here, camouflage object detection. So this was made possible because of the usage of object segmentation, the innovation of object segmentation, as well as also using ResNet as a backbone for this specific task. So this task also uses ResNet as a backbone, where it is really hard to differentiate the target object from the environment. And the the specific networks being used here also depend on ResNet as a backbone. So that is it for our lecture for today. The floor is now open for questions for anyone to ask.
Thank you, Aaron. Sorry. Thank you, Aaron, for the presentation. So as mentioned, the floor is now open for your questions. So siguro I'll ask the first question. I actually like the part of the presentation wherein you showed like the yung I mentioned this already in our meeting, the pass the message part, no, describing the how it was related into the introduction of residual networks. Yeah, this part. Could you like explain or clarify how does this again relate to the introduction or to the inspiration of introducing residual learning in convolutional networks?
Okay. So thank you, Sir Aaron, for that question. So as mentioned, the telephone game is all about trying to pass the message between your group, right? And parang similar din yon sa here yung limitation ng CNN architecture because when you're trying to do an identity transformation, so identity meaning no changes at all between many different groups of layers, many different blocks of layers in one group. Parang similar yon dun sa game of the telephone game because you're trying to just pass the message or just pass the original information along this specific groups. So you can think of this as kapag CNN to, these people are like the blocks inside the group and this image, this message is like the data that is being passed along. So, di ba, when you're trying to pass along the data through these people, sometimes nag-iiba yung message. And that is really hard for, at the same way, that is really hard for CNN architecture to do, which is to keep the original message along the network. So, ang naisip nila, He et al., what if, let's cheat the system a bit, you know? Let's just give this original message to the front. Tapos yun, panalo na every time. Parang ganon. So, that is sort of how I would think of shortcut connections. So, this message, bigay na natin sa harap. And that way, whenever this sort of situation occurs, where it needs an identity transformation, it already has a reference to the original image.
Right. That's correct. That's actually a good explanation of how the the residual learning was introduced into convolutional neural networks. So just to give everyone an idea, residual learning was actually introduced in ResNet, or we call it the residual networks, right? Which is also introduced here in the presentation. So could you go to the part showing the graphs comparing the plane versus the residual networks? Yeah, this one. This is actually a good illustration of the problem that they had back then. So just to give a little bit of history for everyone, back in 2015 when they introduced this, I think it was actually 2014, 2015, around that time. The main idea back then is to increase the number of layers to make the model deeper and deeper and deeper. So when you read this paper on convolutional networks, you'll see that towards the end, they have an experiment of trying to use a residual network, but they have like 1,001 layers. Talagang inoeya nila. But in the official ResNet architecture, we only have 4 variations, I think. ResNet 18, 34, 50, 101, tsaka 152. So it should be 5 pala. 152 na yung pinakamataas. So they tested the bounds, no? Trying to understand, because this work is actually from Microsoft. So they have the hardware to run all of these experiments. They tested the bounds. If they implemented a residual network, but they have like 1,001 layers, what would happen? No? And they also saw that if you have like that large or that deep of a network, there's also a little bit of problem in terms of performance degradation already, even if it's in terms of a residual network. So if you're seeing this figure number 4 in the paper, in the left side, on the left side, the red here and the cyan here, this indicates, or the y-axis indicates the error. So in training a network, we want the model to have less error. So ang inisip natin in our mind, we are thinking that probably if we go deeper and deeper and deeper, the performance of the network or the error should go down. But look at the slide here, the figure that they have here. When they are training a deeper architecture, a 34-layer architecture, the error is much higher as compared with the one with 18 layers only. And just to give a brief history again, before ResNet was introduced, the biggest model is called VGG, or it's still famous right now, the VGG network or the VGG net. The total number of layers there is 19 layers. That's the biggest one. So the experiments here in ResNet, if you are still not implementing residual networks, having 34 layers will not perform as good as 18 layers. So it disrupted the idea that we need to go deep and deep and deep and deep, because it's not in any way performing well anymore if you go that deep. So they introduced the formulation of residual networks. And when they implemented that, then we see here improvements. That a 34-layer network is better than an 18-layer network. Okay? So residual networks, as mentioned in the presentation, is still being used in a lot of things up until this point. ResNet, residual networks, are still being implemented in various tasks in computer vision. So it's really a very important contribution to computer vision. Any questions from the attendees? You can raise your hand or type your questions in the chat. So if you have no questions, can you please raise your hand so that we know that you do not have questions? Okay, I think a large majority doesn't have any more questions. So let me lower your hands. I guess that's it for the talk today. Thank you, Aaron, for the presentation. I do not have any more further announcement because, as I mentioned, this is the last lecture for this term. We are still going to plan lectures that we're going to have next term. And since it's towards the end of the term in our university, I would like to invite all of the students to finish your requirements, use that time. We're not going to have like regular meetings at this point in the term, but please just dedicate your time to finishing your requirements in your courses. And most especially for those who are doing thesis already, make sure to follow the deadlines for that one. Okay, so if there are no more questions from the group, I thank everyone, and I thank Aaron for the wonderful presentation. Thank you, and we'll see you again next term for the next series of lectures and workshops. Thank you.
Thank you, everyone.
Thank you.